So consider a standard worked example for something projected at an angle. Now in this example it's kind of started with the preamble about finding the horizontal and vertical component. Usually that will be part A of the actual question. So remember, this 400 meters per second is at an angle, so it can't go under the kind of horizontal or the vertical heading. And the first thing you've got to do is to find the two components. So the horizontal component, using simple trig, is 400 times cos 30, which is the 346 that we get there. And the vertical component is 400 sine 30, so it's 200. So when we're listing our variables and what we know in this question, we can do things like under the horizontal heading, under the vertical heading. So under the horizontal we can put that V is 346 meters per second. And under the vertical heading we can put that U is 200 meters per second. We don't have a U under the horizontal, remember, because it's constant speed, so we don't have a separate U and a V. We can also fill in under the vertical that because it's a projectile in free fall, the A is minus 9.8 meters per second squared. And then what else we can fill in will depend on what the question is asking us. And in particular, the kind of key points that we might be asked about would be at the highest point here. At the highest point we can fill in that V under the vertical heading is 0. And that can be useful. And if this is a flat surface, like this example here, at the landing point, only if it's flat, at the landing point there's various things we can fill in. We can fill in that the vertical displacement is 0 because it's come back to the same height. We could fill in that the value of the vertical velocity at that point would be the negative of U. So in this case, because it launches at 200 vertical component, then when it comes back down to the same height again, it will be doing 200 in the opposite direction, i.e. minus 200 meters per second in this example. And the time to this landing point is 2 times the time to the highest point, because of the symmetry. But once again, stress these last points here only apply for a totally flat surface. I'm going to move through the rest of the bits of the example here and solve them on separate pages now. So, for the time of flight, the information that we had that we listed in the previous page was U is 200. And we want the whole flight here, so we've also got A is minus 9.8, and here the direction is really important. That acceleration is the opposite direction to the original velocity. And at landing we can put in the S equals 0, and we can use that to find the time of flight. Now, you can solve this with one equation, considering that point. But what a lot of people tend to do is to work out the time to highest point and then double it. It's perfectly valid if it's a flat surface, but you've got to remember to double it or else it's wrong physics and you're going to lose a lot of marks. So now we can substitute in 0 for S equals 200 times T, right, plus a half times minus 9.8 times T squared. Or simplifying the arithmetic, 0 equals 200t minus 4.9t squared. Now one solution to that is t equals 0. That's not surprising. S is 0 when t equals 0. It starts at that height. But the one that we're interested in is when it comes back to it. So the second solution to this is that 0 equals 200 minus 4.9t. So I've divided both sides by t, assuming t is non-zero. And then rearranging that, we get t is 40.8 seconds. That was the first part of the question. In part B, we were asked about the greatest height. So we're still under the vertical heading, but it's not the s equals 0 we're looking at above, but we've still got the u equals 200 meters per second. We know that a is minus 9.8, and at the greatest height we know that v is 0, and we've been asked the value of the greatest height, i.e. the vertical displacement. The easiest way to link these together then is v squared equals u squared plus 2as. So 0 squared equals 200 squared plus 2 times minus 9.8 times s. And rearranging that, you'll get s equals 2040 meters. And so that's your maximum height. For part C, we were asked about the horizontal range. The horizontal range just means the horizontal displacement when it comes back down to land. So we know from up above, from part A, that the time for the whole journey is 40.8 seconds. We know that under the horizontal heading, we've got a constant speed of 346 meters per second. And we've been asked that horizontal displacement. So S equals Vt is our simple formula, remember, for horizontal motion, constant speed, so simple equation. Multiply those two together and you get the range, rounding off to appropriate significant figures, is 141,000 meters. And then for part D, we've kind of got these two wee bits, part D and E. You can flick back to the original question. Part D was asked to find the velocity of the projectile after 10 seconds. So this isn't really kind of one of those key points which we had at the beginning of the highest point or when it comes back into land. This is just another random point in its motion. So the velocity, but it doesn't say which velocity. So we've got to think about both the horizontal and the vertical. Now the horizontal part, so we'll put an h in, it's quite straightforward, that's constant speed, so we know what it's doing, but we'll need to do a wee bit of work with the vertical. So in the vertical heading, once again we know u is 200 meters per second, we know a is minus 9.8 meters per second squared, and we're asked in this example about what's happening after 10 seconds. And we're being asked v. So this is our vertical motion. So we can use v equals u plus at equals 200 right, plus minus 9.8 times 10, which is 102 meters per second. So the vertical velocity after 10 seconds is 102. The horizontal velocity is 346. So worthwhile doing a quick sketch before we combine these. Not terribly well drawn there, not very flat, but you get the idea. And the vertical motion, it's positive, so we know it's still going upwards at this point. And the resultant then that we're after is a single vector, which can replace both of them. And then we can use our standard Pythagoras trig to get this resultant velocity. So from the Pythagoras, we do 102 squared. VR for resultant squared is 102 squared plus 346 squared. Plugging in the values will give you VR is 361. And if we call that angle in there theta, call it x, call it anything you want, is opposite over adjacent, which here is 102 divided by 346, and that gives you theta is 16.4 degrees. So our final answer for the velocity after 10 seconds will be 361 meters per second at 16.4 degrees above horizontal. as shown in the sketch. And then you've got another kind of random question, which was the height of the projectile after 5 seconds. This is quite a long worked example, but just showing you lots of different things that you could be asked. So this is about the height, so it's a vertical displacement. So once again, under the vertical motion, we know that, sorry, that was u, that should be. That u is 200 meters per second. We know that a is minus 9.8 meters per second squared. We know that we're being asked about a time of 5 seconds in this part of the question, and we're being asked the vertical displacement. So the equation which links those together is S equals ut plus a half at squared, and then plugging in the values, 200 times 5 plus a half times minus 9.8 times 5 squared, and then doing your arithmetic, you get 1000 minus 122.5, and rounding to the proper number of significant figures, i.e. 3 is our general rule of thumb. We get that the displacement after 5 seconds is 878 meters, or the height of the projectile after 5 seconds is 878 meters.